about 20 minutes, and you guys are going to start working on a practice problem.
Gotta be
It's
kidding
about
me.
moles versus molarity.
I told you to.
What that means, all that good
Watch the
stuff.
ball stream for
So as you may remember, moles equal how many molecules of something you have. The moles is a really big number. So 6.2 times 10 to the 23rd. And it's such a big number because it counts such small molecules and atoms and all that good stuff. So this is just do right there. And we have this formula, moles equals mass over formula weight. So no need to write that down. You probably already know that good stuff. You might notice I wrote the word pure right here. So we've been using this equation for several weeks now. So here's the thing that I failed to mention, or I failed to mention. That equation only works for pure solids, liquids, and gases. So the whole moles equals mass over formula weight. That's only if you have a pure substance. Only if you have a pure substance. So a liquid, for example, is a state of matter that's a pure substance. So like right here I have pure H2O, this is distilled water, okay? That would be a liquid, a pure substance. So moles equals mass over formula weight works for that pure water right there. It'll also work for like solid substances, so basically anything solid is going to be pure. So salt, for example, we can use that formula weight of 58. Or if we know the mass of this pure distilled water, we can know how many moles of water we have. So let's pretend I poured exactly 58 grams of salt right here. So like, okay, I have 58 grams of this, it's exactly 1 mole. Or in other words, there's 6.02 times 10 to the 23rd, and HCl molecules right here in this little tray. Okay? And so, the reason why this works is because everything in there is going to be exactly the same. There's going to be nothing but NaCl's in that little plastic disc. There's going to be nothing but H2O's, that big beaker. And you know which formula weight to use accordingly. Now, here's an issue though. What if I did something like this, where I take my salt and I pour it into the water? Now which formula weight do I use? It's the 58 of salt. Do I use the 18 of water? Like, what do I do with this?
Calm down. Friday afternoon.
He's salty. Huh? This guy. Yeah, so which formula weight do you use? Do you use the 58 for salt? Like, well, there's water in there. Okay, so you use 18. What's that?
You add them together.
So you use the formula weight of 76?
Yeah.
Interesting idea. I heard the average too. Like, wait, could you just use the average to find the middle ground between 58 and 18?
I'm right.
But how could those work exactly? It's like, well, wouldn't I need like exactly the same mass of both of them for that to work potentially?
No.
You do a ratio of
You don't know what you're talking about.
A ratio is the solution to our problems. We're not quite there yet. Because
I was somewhat right.
I can't actually get like 100 grams of salt into 100 grams of water. Like, the water won't dissolve that much at a time. And so, unless we could always do it that way, it won't really work. Not to mention, that's not the kind of solution that we want lots of times. Sometimes we want one that's a lot more diluted than that. And so, that is what brings us to the idea of molarity. That's why we need molarity. So if you look up in my cabinets on that side of the room, there are dozens of bottles of stuff that we use for labs throughout the year. Every single one of those is a solution. And every single one of them has more than one thing in it. So the whole moles equals mass over formula weight won't work for any of those. And we love these solutions in labs because the kinetics solutions allow molecules to run into other molecules much more easily. Okay, speeds things up quite a bit. And so we need to be able to figure out what to do with solutions of stuff. Now remember, a solution, by the way, by definition, is more than one thing. It's a mixture. So pure water, that's a liquid. But tap water, where it's got the ions and the minerals mixed in, that's a solution. Okay. So molarity is a ratio of moles per volume. So it is a ratio. Comparing moles to volume, there's a relationship there. And sometimes we say the word concentration. So, in layman's terms, we talk about concentrations, okay? Those are really molarities of something. And this is only for solutions, okay? This only works for solutions. You're somewhat familiar with this concept already. So I have 3 bottles of copper sulfate up here. One's pretty translucent, one's kind of medium, and one's pretty dark. I have 3 bottles. These are what I dissolved into different solutions. Now this bottle barely has a copper sulfate in it. Which one of these do you think corresponds?
The darkest one.
Think this goes to the darkest one?
Yeah.
So this bottle, with just a little bit of copper sulfate in it, like solid copper sulfate, which one of these bottles do you think it corresponds to? The lightest, the medium, or the darkest?
Oh, I got confused. Lightest.
Yeah, it's the lightest. And the one with a bunch of copper sulfate corresponds to the darkest, right? This one's the medium. And that's exactly what happened. So I dissolved about this much copper sulfate when I made this solution, whereas I dissolved a whole bunch to make this solution. So this idea of concentration, how much stuff you have in each solution, you're already familiar with that idea, but molarity is where we put actual numbers on it in terms of moles. So it's basically how many molecules are swimming around in the solution. You don't have to write that down, but that's the idea. How many copper sulfates are swimming around in each one of those solutions? And so we kind of talked about these. Those different molarities are 0.1, 2.0, and 4.0. That capital M stands for molarity. So that's where those labels come from. You've already seen those labels a couple times in various labs throughout the year. You just didn't realize that's what they were referring to. So earlier this week we talked about 6 molar HCl. We're like, well, I don't know exactly what that means, but that sounds dangerous, which it is. And that's because the concentration was 6. It's pretty high. Pretty high. So here's your equation that you should absolutely write down, put a big star next to it, whatever. Molarity is equal to the moles of stuff, whatever it is you're working with, divided by the volume of the solution. Moles of stuff divided by the volume of the solution. Now I'm going to go ahead and put in parentheses here, next to the volume of the solution, a capital V and a subscript capital L. That symbol means the volume in liters. That means the volume in liters. You'll see that on different answer keys. That's a variable, all right. Volume in liters, VL. And that volume, by the way, is the total combined volume. So I know that salt has its own volume, water has its own volume. When you mix those together, their total volume, like all the volume added up, that is the volume of your solution. Okay, your total volume. So we take a look at the units for molarity equations. The capital M, shocker, plot twist, stands for molarity. Not moles, molarity. And remember, that's just a ratio between moles and liters. So capital M is not a symbol for moles. So I could say, hey, this is a 4.0 molarity solution of copper sulfate. Or I could say, this copper sulfate has 4 moles per liter. Those are 2 ways of saying the same thing. Talk about the concentration, the molarity. And the volume needs to be in liters. This is very important. It's got to be in liters. That is a key piece of information. The volume has to be in liters. Okay? Now the problem is, so if we have these 3 measurements in milliliters, not to be a stickler, but I'll be giving you guys problems with milliliters all the time. You're going to convert them into liters and back out of them and all that good stuff. Mr. Filter, why don't you just have everything in liters? Because in this lab setting, we're going to be working on a fairly small scale. All of your lab equipment, like literally all of it in the drawers and those burettes you guys are going to use for lab next Monday, they're all in terms of milliliters. Because the liter is actually pretty big. And so everything you're going to do in lab, including Monday and Tuesday of next week, will be in milliliters. So it's just the way that it is. Like you're working on a small scale, so you're just going to be working with milliliters. And so we're going to have to get used to going from milliliters to liters and liters to milliliters. It's not very difficult.
You just move the decimal.
What's that?
You just move the decimal.
Yeah, pretty much just move the decimal. Now to be clear, okay, so you think of a millennium, that's 1,000 years, right? So milli is in reference to the idea of 1,000,
Oh.
okay? So a milliliter, 1,000 milliliters is 1 liter. In other words, a liter is 1,000 times bigger than a milliliter. Now, mathematically speaking, to convert milliliters to liters, you're really just moving that decimal 3 times to the left. I don't want you to memorize that. I want you to understand I'm really just dividing by 1,000, okay? Which does move the decimal 3 spots to the left. But I don't want you to mindlessly move the decimal. I want you to understand I'm dividing by 1,000 here. So 1,475 milliliters is only 1.475 liters. And 56 milliliters is only 0.056 liters. And 2.94 milliliters is 0.00294 liters. You'll notice that if Mr. Filter gives you the 2, the point, the 9, and the 4, you should keep all 3 of those. So if you change it to liters, since you're not doing any calculation there, you're simply just converting the units. You can just keep it 0.00294. Like you want to keep that 4 on the end, even though it's a third sig fig after the decimal. Because you might as well, I gave it to you. It's not like you calculated that, I just gave it to you. So please keep that in mind. It's a two-way street. So you might have to convert milliliters into liters, but then you might have to convert those liters back into milliliters eventually, once you do a couple calculations. So just keep that in mind, whether you're dividing by 1,000 or multiplying by 1,000. The number of milliliters will always be a lot higher than the number of liters, because milliliters are pretty small. All right. So let's see here. Let's say we have a goal to prepare 1 liter of a 1 molar salt solution. Let's say this is our goal. And you can put your pencil down for a quick second. Let's say we were just trying to make 1 liter of a 1 molar solution. You would have to know how many moles you have, so mass over formula weight type of situation. But you also have to be able to talk about the molarity. So you're going to be using both of these equations for a lot of different problems. So get used to using both of these in the same problem, which is why we did so much practice with the first one, so that one can be more on autopilot as you put your attention on the molarity equals moles over volume at this point. And you'll have to use formula weights, all that good stuff. So let's go ahead and put some numbers on this. So again, molarity equals moles over volume. Now, if you rearrange that equation, moles equals molarity times volume, where did that come from, Mr. Pilcher? Well, if I multiply both sides by volume in liters, again, VL is volume in liters.
Should we write this down?
You might want to write this part in red down. So volume cancels out right there. And so molarity times volume in liters is equal to the moles. And that's only for solutions, okay? That's only for solutions. Which if you ever forgot that and you're working with a pure substance, you realize your mistake when I asked you to plug in the molarity in the volume, like, oh, wait, I don't have either one of those. Okay, I must be using the wrong equation. So you can still solve for moles like we have been doing, but the equation is a little bit different when you're working with a solution. So here's the type of question I might ask you on a quiz or test. Which has more molecules of NaCl? I'm going to walk you guys through this one. 10 grams of solid NaCl or 50 milliliters of 3.0 molar NaCl. Which one has more molecules of NaCl? Well, these are clearly apples and oranges. Okay, how am I supposed to 10 grams versus 50 milliliters? Like, how am I supposed to know? You're going to have to get them speaking the same language, or have to put both of these in terms of moles of NaCl, and then we can compare directly, no problem. So on the left, hopefully, this is something that you guys can do in your sleep. Hey, it's a pure substance. Okay, it's solid NaCl, pure substance. So what equation can we use? Moles equals mass over formula weight, right? Because it's a pure substance. So my moles will be equal to my mass, which is 10. What's the formula weight of NaCl? 58, yep. Sodium's 23, chlorine's 35, 23 plus 35, 58. Boom. So I've got 0.17 moles of NaCl over here. Nice. Now I just have to get my solution over here in terms of moles, and I'll be good to go. Is this a pure substance?
No.
No, so we have to use our other equation using molarity. So the moles of a solution are equal to the molarity, that concentration, times the volume, okay, in liters. So when we're plugging this in, moles will be equal to 3 times 50, okay? What's wrong with that? It says 50 right there. Can you not read that?
It's milliliters. You need to get it.
Oh, okay, yeah. It's in milliliters. Here's a little tip for you. The moment I see milliliters in something, I'm like, not gonna mess with that noise. No, I convert it to liters before I even do any math, just so I don't give myself a chance to make a mistake later or forget about it. Yep. Nice catch. So, all I have to do is multiply those two together. I'll find I have 0.15 moles of NaCl in that solution. So it looks like I have more molecules of NaCl hanging out in those 10 grams of solid stuff than I do in the 50 milliliters of this solution. Please notice that if you forgot to convert the 50 milliliters into 0.05 liters, you would have got 150 moles over here, and you would have circled the one on the right. I will intentionally give you problems like this, where if you forget to convert, you'll make a mistake. Does that make sense? And it's not to like come at you, it's just in laboratory it's really important that you don't use 1,000 times too much solution or 1,000th the amount of solution. So you gotta make sure we take care of it on paper before we get to lab. Alrighty, not bad. Okay, we're done with notes. You're finding this worksheet in your packet. We're gonna do a couple problems together here.
Before we had our test yesterday, I asked like 3 people, like seniors, if they remembered how to do soy geometry, and all of them said
All of them said no. Probably depends on the senior. So this soy problems worksheet number 2. This is in your packet. If you find something called titrations, you've gone a teeny bit too far. Should be right before that. Alright. So this first problem says a solution is prepared by dissolving 15 grams of nickel nitrate. So this person got 15 grams of nickel nitrate. They mixed it in with water, and the total volume at the end was 250 milliliters. What is the molarity? So what's the concentration of this solution? Okay, cool. Well, before I really do anything, this noise, 250 milliliters, no thank you, 0.25 liters. Okay, not going to deal with that, because once I get into doing a bunch of math, I don't want to give myself a chance to forget to convert this later. So I'm just going to do it now. Alright. Now, please remember, molarity is equal to moles over the volume in liters. This question is asking you for molarity right here. So that means I'm going to have to know the moles, I'm going to have to know the final volume. Well, I know the final volume is 0.25, that's given to me in the problem. Sweet. Am I told the moles in this problem? No. So I can't get the molarity. I have to get the moles first in a first step, and then I can find the molarity in a second separate step. You will notice on my blue answer keys, which you guys can take a look at those more in a minute, I am meticulous with my organization, and I draw out everything, I separate my steps, I label everything, because there are so many numbers on some of these. So the first step is I gotta find out how many moles of nickel nitrate I'm even dealing with. Hey, it's 15.0 grams of solid nickel nitrate. Is that pure? It is. So what formula can I use? Moles equals mass over formula weight. So this is business as usual. My moles will be equal to mass over formula weight. And so my moles of nickel nitrate will be the 15 grams divided by the formula weight. Well, nickel is a 59, plus the 2 nitrogens, which are 14 each, plus the 6 oxygens, which are 16 each. Adds up to $1.83. And so I have this many moles of nickel nitrate. Notice the label and everything. So now that I know how many moles of nickel nitrate I have, I can plug that into my molarity equation. I can plug that into my molarity equation. So molarity is equal to moles over volume. Well, my moles is 0.082. My volume, now this is where people are going to actually like divide by 250 because they didn't convert it at the beginning. They forgot. It's 0.25. If I go ahead and plug that in, I'll find that 250 milliliter solution with 15 grams of nickel nitrate dissolved in it will be a 0.33 molar solution. I put a box around it just like that. We're going to do one more problem together to help you guys be prepared for the lab on Monday and the lab on Tuesday where we are doing titrations. So question 4, we're going to scroll down to question 4. That's just like the lab on Monday and Tuesday. So it says, first of all, consider the following balanced. Oh, look at me. I gave you guys a balance equation. Not always the case, but I'm telling you this one's balanced, so you don't have to worry about it for now. Equation says a student adds 42.6 milliliters. No. A student adds 0.0426 liters of the 0.22 molar hydrochloric acid solution to a flask. She determines that it takes 0.04 liters of a sodium hydroxide solution to neutralize HCl. This word neutralize, you may have not seen that before. That just means like react completely. So they needed that much sodium hydroxide to use up every last drop of the HCl, to react completely, to finish the reaction, okay? Where they meet in the middle, whatever you want to think of it. And so the question is, what is the molarity of the NaOH? So again, if we want to know the molarity of something, we need to know the moles and the volume. I know the moles, I know the volume of NaOH, but I do not know the moles of NaOH. So that's objective number 1. Find the moles of NaOH. Well, okay. Let me break down everything I have. And you'll notice I do this on the answer key. You don't have to do it just like I do, but I'll show you how I do it on the answer key. I write down my molarity and my volume for everything in the reaction. So we're told I have 0.0426 liters of hydrochloric acid, and that concentration is 0.22. We're also told we use 0.04 liters of NaOH. But this concentration, that's what we don't know. So I put a little question mark next to it. That's what we're being asked about. Okay. So in this reaction, we're going from the HCl to this guy. Mr. Coates, how did you know we're going from the HCl? Well, that's the only thing we have information on, so we have no choice. That's where we have to start. So, some of this will look familiar to a mass-to-mass calculation. It won't all be the same, but it'll have some similar vibes. I'm going to start by calculating the moles of HCl, as I normally would. Calculate the moles of what you started with. Well, my moles are going to be equal to the molarity times the volume, right? Because it's a solution. So moles is equal to 0.22, that's my molarity, times my volume, which is 0.0426. Alright, so it looks like I have that many moles of HCl. I got that many moles of HCl. Now, what's the ratio of HCl to NaOH? It's 1 to 1, right? It's 1 to 1. So I have a 1 to 1 ratio. So that means I'm just multiplying by 1. So how many moles of NaOH do I have? You got it. 0.0094 moles of NaOH. And so, normally in a mass-to-mass calculation, this is where it'd be like equals mass over formula weight. We plug in our formula weight, and we're on our way. But this is a solution. It didn't ask me for the mass. It asked me for the molarity. Well, okay. I mean, I can do that too, because I know the moles now. It's 0.0094. The molarity is what I don't know, but I know that the molarity times the volume, which I was told was 0.04, will be equal to that. So what do I have to do to both sides right here? To get molarity by itself? You got it. These will cancel out here. So my molarity will be equal to 0.0094 divided by 0.04. If you plug it into your calculator, you will find that the molarity is 0.24 NaOH. And there goes the box because I'm a model student.
What if you want a model?
Maybe you circle it instead.
No, just kidding.
Circles are fine. Okay. On Monday, you will be doing a titration of some vinegar. So you're basically going to do this exact setup with vinegar. You're going to find out the concentration of that vinegar. So you're going to be doing this calculation. The day after that, you're going to do a titration of an unknown substance. It'll be the same type of calculation. And guess what's going to happen after you do lab a couple of times?
Oh, we take a quiz on it Wednesday.
You got it.
Oh.
Okay? Yes, sir.
Will we do equations at our titration stations?
At your titration stations?
Yeah.
Equations at your stations?
Sorry.
Titration stations? Probably. Alright, so what's going to happen is, I want you guys to get cooking on this. The answer key is blue. In the meantime, I'll pass back your guys' quiz from yesterday. Let's get it cooking.